This marks the final video for Chapter 26, Nutrition and Metabolism. Here we're going to look at the stages of metabolism and discuss the management of nutrients and how they are used for either ATP production or storage. So keep in mind the previous video we looked primarily at how ATP is generated using glucose, a carbohydrate, as a source of energy. You're going to see throughout this video how there are alternate sources of ATP, as well as the processes by which these molecules can essentially convert back and forth. So what I would recommend doing as you start this video is keep a list of process names. You're going to want to make sure that each one is very clear, that you understand when each process is used and what it does very specifically. So if we just essentially summarize what we're looking at here, at this point, we have already described stage one, so digestion in the GI tract, and how all of those, the monomers of a protein, which are the amino acids, monomers of carbohydrates, which are your glucose and other monosaccharides, and of fats, those were the glycerol and the fatty acids. We saw how those could all be formed and then, of course, absorbed and transported through the bloodstream. And then what we did is we took a look here at how glucose itself could go through glycolysis and the Krebs cycle, and then finally oxidative phosphorylation to form ATP. Now what we do in this video is we talk about the timing of those events, and then as you can see here, we start to play in on how the amino acids and all those fat components here actually tie into these processes. We're going to look at two different events in which these processes are grouped. The first is the absorptive state, and the second will be the post-absorptive state. Here in the absorptive state, this is about a 4-hour window that's occurring during eating and then in the hours immediately after eating. And this is when you're going to see a large amount of very small nutrients that have been absorbed into the blood. So lots of circulating amino acids, circulating glucose, and circulating glycerol and fatty acids. And so what you do overall here is you utilize more anabolic reactions than catabolic reactions. And that makes sure that nutrients are used and stored if they are in excess. So that means that anabolic reactions are taking amino acids and forming proteins. Anabolic reactions with glucose form glycogen. And anabolic reactions of glycerol and fatty acids form your triglycerides. Keep in mind that amino acids in excess will not be stored, but we will see them later on in how they can be used through gluconeogenesis and oxidative deamination to help form energy. And so we're going to start here by just recapping what's happening with your carbohydrates. So of course, recall glucose is the primary source that we want to be using. Your fructose and galactose can be converted to glucose in the bloodstream. And for the most part, in a perfect world where all of your energy is balanced, you would see that all that glucose essentially is going to be immediately catabolized for ATP production. Right? So there it is, glucose making ATP. However, you do end up with excess glucose, and you want to make sure that that is stored. Now, what's important here to recall is that we have talked quite a bit about diabetes mellitus in this class. Step 3 is where diabetics are impacted, right? Because you can't store the glucose the way that you need to. We're going to look at the effects of insulin here in just a second, but just a heads up. Now, glucose itself is going to be stored as glycogen. That's the first thing. And the second thing here is that process, again, is known as glycogenesis, so the formation of glycogen. In this graphic here, what you are looking at here is a cell that could be in the liver or the kidney, and we're looking at what's going on with the purple arrows. So glucose within the blood are entering this cell, and they're being stored in the form of glycogen. Now, this happens through a number of steps, known as glycogenesis, in which you would actually see hexokinase itself actually converting glucose into glucose 6-phosphate, and then finally into G1P, UDG, and then of course into glycogen itself. What's most important to me here is that you understand these bolded terms, and that of course you recognize that this enzyme hexokinase that you see right through there is responsible for this. This is going to be present in all tissue cells so that glucose itself can actually make it into these cells to either be stored or used. Now the major storage sites we're going to see are the skeletal muscles and the liver. So now we take a look at what's happening with carbohydrates during this step, or continue to talk about carbohydrates during this absorptive state. So any excess glucose that's circulating does not just have to be stored as glycogen. Some can be stored as fats. And so while this chart here looks pretty scary, you'll notice a lot of it's very familiar. What they're showing you is this process of glycolysis that's taking place, where glucose, again, is forming G3P. Keep in mind that G3P is the same thing as pGal for us. And then, of course, pyruvic acid. Pyruvic acid converted into acetyl-CoA through the transitional phase, and then finally being used in the Krebs cycle and the electron transport chain to generate large amounts of ATP. Okay, so that's what's very familiar there. Now, what we see is that if you have a lot of excess glucose, then that pGal right there, that G3P, can actually be converted into glycerol. Now, this is done through a process named lipogenesis, so the formation of fats. Because as you begin to form glycerol, then that glycerol itself can form triglycerides and essentially be stored as fats in adipose tissue. Now, likewise, the acetyl-CoA that's formed down here, any excess acetyl-CoA can be converted into fatty acids here through beta oxidation. And that's the process there. And those fatty acids themselves, once again, can combine with glycerol to make triglycerides. I know you can see the words lipolysis here. Ignore those for now. What that's referring to is what the blue arrow is showing you. So lipolysis is going to be the reverse of everything we're talking about here. So lipogenesis and beta oxidation helping us to form glycerol and fatty acids from excess carbohydrates. The idea here is that this is going to be enzymatically regulated, and most of these enzymes are in the liver and the adipocytes, and this is, of course, where these fats are going to be stored. Now, the idea here is that your excess triglycerides can be stored as long as ATP levels are really high. And of course, remember that's not the only way that lipids could be used. You have your lipoproteins that are transporting excess cholesterol and other lipids to many cells within the body. So cells that are actually making steroid hormones, as well as those cells in the liver that make bile salts. So we transition then from the lipids all the way here to amino acids. So amino acids are important because they are used for protein synthesis. Recall that amino acids will assemble into polypeptides, and those then can coil up to form a functional protein. Now, within the liver itself, the liver is going to form what are known as keto acids with these amino acids. And what's really important here, and I should have this higher in the notes, is that there's actually no storage sites for excess amino acids. So even if you have storage for fats or storage for excess glucose, amino acids don't work that way. And that's why we have to discuss the formation of keto acids in the liver. And so in this image here, you can see what would be happening if you happen to have excess amino acids. So again, these excess amino acids would actually go through a process here called deamination and then transamination, as it says right here, with the end product being a keto acid. Now, a keto acid can seem like a pretty unknown concept here because we haven't actually discussed it much. So I write down here the keto acids themselves can be modified for use as acetyl-CoA, pyruvic acid, and oxaloacetic acid. So really just think of keto acids as all those things that can essentially be utilized as part of the Krebs cycle. Right? So these are good things. We can actually use those. Now, during this process, however, once you form the keto acid, you do give off a specific amino acid known as glutamic acid. And that has to go through what's known as oxidative deamination, where you actually remove the amine group, which is written as an NH2, from that, and you convert it to ammonia. Now, ammonia itself, if it begins to build, is very toxic and dangerous. But within the liver, you have the ability to create urea from that ammonia. And urea is far less toxic. It can be managed really well, especially in the kidneys. And the kidneys can just eliminate that urea in the form of urine. The problem comes when an individual has liver damage, liver cancer, cirrhosis of the liver, because that eliminates the ability of many of the hepatocytes to facilitate oxidative deamination. And so those are going to be individuals who see a buildup of ammonia and they don't actually produce enough urea during this process. So again, that's the idea. You have deamination or transamination is what we look at here, and then oxidative deamination. And that's going to help make sure that any of those excess amino acids that aren't going to be used can be converted into urea, right? And then you can eliminate that safely. Now, throughout this process, we're going to find that insulin is a primary regulating hormone of everything in the absorptive state. So just to recap what insulin does for us, whenever you see high levels of blood glucose, that's what's going to stimulate the beta cells of the pancreas to actually raise blood insulin. Now, what we're most familiar with right here is that that high level of insulin is going to increase the glucose diffusion into tissue cells. What I'm adding here that we haven't discussed a whole lot is at the same time that also increases transport of amino acids into tissue cells. And so not only is insulin boosting glucose storage, but also the formation of proteins through protein synthesis. Now, there's a number of processes that are associated with this, and that's going to be facilitated in part by insulin production. So insulin in itself right here can actually help to convert glucose into glycogen. And so what you see here is that insulin enhances glycogenesis, right? So formation of glycogen there. At the same time, I mentioned that it's enhancing protein synthesis right through there, right? What's important is that it can also induce lipogenesis. I don't mention it, but it can actually help with the storage of fatty acids and glycerol. Now, it does tend to inhibit the breakdown of glycogen itself. And so I have glycolysis written here, and I'm realizing this should say glycogenolysis. So I'm back. I paused and corrected that. That should say glycogenolysis. It won't necessarily inhibit glycolysis because that's important for utilizing this glucose for ATP production. All right, so that's the basic idea behind what insulin is doing. Now, at the same time, I want to pay attention to here to how insulin is actually increasing glucose absorption into a cell. Now, that's going to do so by actually increasing the amount of what we call a glucose 4 transporter protein called the GLUT4 transporter protein. And it looks a little something like this. Whenever insulin binds to these receptors in a cell, then that receptor does a number of things. Here are all the effects on protein synthesis, growth, lipid metabolism, glucose storage. But what it also is doing is it's essentially taking GLUT4 transporter molecules and it's embedding them here into the membrane. And so where you might just have a few of these GLUT4 transporters, the presence of insulin causes you to increase the number that you have in the membrane, making more spaces here for glucose to actually be diffused into the cell itself. Okay, and so the idea there is not necessarily that we're trying to open or close existing transport molecules, but we want to add more so this cell can pick up more and more and more circulating glucose. So as a recap of the absorptive state, again, this looks like a scary diagram, but it walks through all these steps and gives you here a lot of the names of processes that we've discussed. So again, let's assume we've just finished a meal, right? Remember, absorptive state is during that period of eating and then for about a few hours after. The glucose that's circulating could go ahead and be used to make ATP. Excess glucose then can be stored in the skeletal muscles as glycogen through a process called glycogenesis. It can also be stored here, right, in the liver as glycogen, also through the process of glycogenesis. So that's it. You either use it first or you store it as glycogen. The second thing that we, of course, see happening is that glucose itself can go through lipogenesis, right? We said lipogenesis could convert that pGal molecule into glycerol, so it eventually forms triglycerides. And at the same time, you could see the acetyl-CoA contribute here to the formation of fatty acids, and those combine with glycerol to make that triglyceride. So first you store glucose as glycogen, then you store your excess glucose as triglycerides. You also see right over here that the amino acids that have been picked up, again, this is stimulated by insulin production. The amino acids themselves could enter these tissues, right, and synthesize proteins here in the skeletal muscle, here in the liver itself. Finally, what we're going to see is that those amino acids themselves could go through that transamination and oxidative deamination process to make keto acids. Those keto acids could enter the Krebs cycle, as we said earlier, to form ATP. And finally, of course, we take a look here at the triglycerides that are actually being absorbed from your diet, and those, not just those that are formed from glucose, as we see happening right over here, but just your triglycerides that you absorb, that you store on your own, and adipose tissue. That's your absorptive state. And so what I would do is I would pause this video and stop and walk through these steps in the notes and make sure it's all clear before you move to the post-absorptive state. So the post-absorptive state is more or less the opposite of the absorptive state itself. So here we're seeing mostly catabolic reactions. So all those proteins we formed, they're broken down into amino acids. Glycogen being broken down into glucose, and triglycerides pulled out of storage and broken down into glycerol and fatty acids. The goal here is to make sure that falling blood glucose levels stop falling and stay within a healthy level, somewhere between 70 to 110 milligrams of glucose per milliliter. Remember that at all times you need to have glucose available for ATP production, and not necessarily have to, but that's ideal. Right? So the idea here is that while insulin was really important for our absorptive state, here you start to see glucagon taking over during the post-absorptive state. Recall, glucagon was important for helping us to pull glycogen out of your glucose out of your cells so that it could circulate here for ATP production. We also see here that increased sympathetic stimulation of body tissues is important for this, and so that means that epinephrine and norepinephrine are going to play a really large role in this process. Okay. And so here with the post-absorptive state, we more or less get a play-by-play of everything that's happening. And so the numbers that you see are showing you in order how the body begins to harvest these molecules. And so just as a quick summary, because we'll see this image again at the very end, we're going to start here with glucose. Glucose from glycogen that's been stored is the first thing we're going to try to use in the post-absorptive state. We see then that the second thing we want to do is pull glucose from stored glycogen in the skeletal muscles. So first here in the liver, then here in the skeletal muscles. After that, that's when our body moves to metabolizing stored fats. And then number 4 is where we start to see our body start to metabolize proteins that exist. The goal again is to make sure that the brain, above all, has adequate glucose. But as we're going to see, the brain doesn't have to use glucose, it can use other sources. So let's go ahead and talk through these processes in order of when they would occur. All right, so again, looking at this post-absorptive state and focusing on carbohydrates. So as these blood glucose levels begin to fall hours after you've eaten, right, glucose is harvested in the following order. First, glycogenolysis from the liver. So recall that glycogenesis is when you stored the glycogen. Now lysis means you're breaking it down. And so this is going to rely on an enzyme known as glucose 6-phosphatase. Now this image looks familiar because when we studied the absorptive state, we were looking at what was happening in the purple arrows. We took glucose, used the enzyme hexokinase, and we stored the glucose as glycogen. And this could be done a number of places. However, we find this glucose 6-phosphatase enzyme right there is only present in a few cells in the body, the liver, of course, being one of them. And so the idea is the liver is one of the few places where you can actually fully break down glycogen into glucose that's readily accessible. Now, when you look at step 2 here, after you've started glycogenolysis from the liver, the skeletal muscles then start to contribute to glucose circulation. But skeletal muscles lack glucose 6-phosphatase. And so the idea here is that glycogenolysis begins in the skeletal muscle. You basically begin to break down glycogen, but you get stuck here at glucose 6-phosphate. Glucose 6-phosphate enters the blood instead of just blood glucose, and it transports to places like the liver where it can be finalized in its conversion to blood glucose. So then, of course, you've finished up your breakdown of glycogen, again known as glycogenolysis, and now you can start to burn fat. So lipolysis is the process we look at here. Recall that lipogenesis was the formation of stored fat, but lipolysis, again lysis, is going to be the opposite. It's the breakdown. And so we go back to this image. We studied it a few minutes ago. And of course, we were looking at what happens when you take glucose, pGal, and acetyl-CoA and you run them in this direction to store fats. But now that we're in the post-absorptive state, we want to move in the opposite direction. So again, here through lipolysis, we find that glycerol can be used to generate pGal here in glycolysis, and that these fatty acids can go through beta oxidation to form acetyl-CoA. Okay, so it's essentially just the reverse of what we studied earlier. Now, one thing that I want to note here, because this is a pretty important topic, acetyl-CoA, as we just mentioned, right, can be formed, right, through beta oxidation from fatty acids. And the goal of having acetyl-CoA present is so that it can enter the Krebs cycle. Now recall that in order for the Krebs cycle to run, acetyl-CoA has to bind to your pickup molecule, oxaloacetic acid. Now, if you've got an individual that doesn't have enough carbohydrates in their diet, this actually becomes a problem because you tend to not have enough oxaloacetic acid. And so acetyl-CoA in an individual with too few carbohydrates in their diet, acetyl-CoA reaches the Krebs cycle and can't be used. It has no oxaloacetic acid to bind to. And so at that stage, acetyl-CoA that can't be used is converted into a ketone body. And this process is known as ketogenesis. And so ketogenesis is actually going to form ketone bodies, and this is done by the liver itself. Now this happens all the time, and it is a really natural process in the bodies. However, we've heard a lot nowadays about the ketone diet and ketoacidosis, so I just want to make sure that some of these terms make sense. So to begin with here, this process of ketogenesis does not always cause ketosis, right? But ketosis in itself is just when you start to have excess ketone bodies in the bloodstream. Now that in itself is not really a bad thing, but if this is in too great of an excess, this can lead to ketoacidosis. And ketoacidosis is a condition in which the body has become way too acidic, the pH is too low, and you can start to see organ failure and mental issues begin to occur. So again, this idea of an Atkins diet, which is low carb, or even just like the ketone diet, which is low carb, those are not bad in themselves. The brain itself can actually start to use ketone bodies as an energy source, even during periods of fasting when glucose is not readily available. So the brain does this readily and it does this well. Again, what becomes a problem is when you have ketosis for too long, and that leads to ketoacidosis. Just a little background there. The keto diet was actually designed to regulate epileptic seizures in children, and it's actually a diet that does very well there. It is a diet that apparently is very hard to follow, so you probably won't see me jumping on that bandwagon anytime soon. I like my ice cream too much. But that's the idea about what's happening there with ketone bodies and the keto diet. And then, of course, we take a look at the final stage here of the post-absorptive state, and that's catabolism of cellular proteins. Now, recall, you don't just have excess proteins that are floating around or excess amino acids that are floating around. At this point, any amino acids that you have in the body are being used in some way. So this needs to be the last step. Right? If you at this point are breaking down cellular proteins, you're essentially cannibalizing the body itself. And so this tends to happen when you've had fasting for a very long period in time. It can be associated with tissue wasting disease and starvation. And so this can occur, but it doesn't need to occur in high levels on a daily basis. The idea here is that this process is going to be associated once again with oxidative deamination so that you can actually utilize these amino acids. And then by using them, you're actually going through a process called gluconeogenesis. It literally means making new glucose. And I didn't give you guys a standard definition in your PowerPoint, but I've written it here in red. So gluconeogenesis is the synthesis of glucose from amino acids that we're talking about here and from glycerol. And so the idea here is that, once again, you are essentially taking amino acids here in your diet, and from them you are generating keto acids. And so those keto acids are pyruvic acid and acetyl-CoA. Now, the idea here is those could go on to enter the Krebs cycle, but if you wanted to go on and produce glucose at this point, because those glucose levels are low, then the only phase that does this well are the formation of pyruvic acid. So pyruvic acid has the ability to go back and form more glucose, but acetyl-CoA really can't do that very well. So again, if you've got really low carbohydrate levels, not enough oxaloacetic acid, then this process too is going to be coupled with the formation of ketone bodies. So like we said earlier, while insulin was very important in the absorptive state, now glucagon, and as we mentioned too, epinephrine and norepinephrine, these are very important in the post-absorptive state. So let's just recap here what glucagon is doing. So as you start to see a drop in plasma glucose, again, this is the post-absorptive state several hours after eating, then you're going to see alpha cells of the pancreas begin to secrete glucagon. So glucagon, as we said, is what's going to be responsible for glycogenolysis of the liver, helping to withdraw glycogen stores. It's also going to be important for gluconeogenesis. So where you start taking some of the glycerol that you have from your triglycerides, as well as the amino acids that you have in the form of protein, and using those to create glucose. And so with glycogenolysis and gluconeogenesis, you start to see an increase in plasma glucose so that your body can begin to use that for ATP production. And now, of course, glucagon itself stimulating the breakdown of fat, that increases floating fatty acids and glycerol, and those, of course, can be used by your tissues to generate ATP on their own. And that's what we call glucose sparing. This is a negative feedback regulated mechanism, so once glucose levels are high enough, then you can actually stop secreting glucagon. So again, just to recap, what you saw happening here is several hours after you've eaten, first you have glycogenolysis from the liver, and of course then from the skeletal muscles. And after that, you start to see a breakdown of fat here, triglycerides, and then of course you start to see a breakdown of protein. One of the things I'd like for you to be able to do is tie in the hormones we've learned this semester and how they tie in with this process. So we spent quite a bit of time just now talking through insulin and glucagon, and here this of course includes epinephrine from the discussions that we've had. You'll see here that growth hormone couples some of the functions of both of the absorptive and the post-absorptive state. Growth hormone is important for amino acid uptake because it's building proteins, right? There's tissue growth that's occurring. And so it's incorporating amino acids into tissues so that it can stimulate protein synthesis. At the same time, the post-absorptive mechanisms that it uses are lipolysis and fat mobilization, as well as gluconeogenesis. And this is because while growth hormone is helping to build protein-based tissues, it's also got to make sure you have an adequate ATP production to fuel the body that's developing. So you look at thyroxine next, right? So thyroid hormone. So this is going to increase glucose uptake by cells themselves. And then, of course, glucose catabolism for energy, that's just glycolysis, generating ATP. Same thing here, generating protein synthesis and a breakdown of fat. So this is where it couples growth hormone quite a bit. Cortisol itself is very similar to epinephrine and glucagon over here. So very important at withdrawing stored energy to make sure you have adequate ATP. And testosterone, of course, is going to be important for helping to stimulate protein synthesis and tissue growth. There's a few homeostatic imbalances that I tie in here at the very end, just because they're usually well known. PKU is probably the best known of these. It's phenylketonuria, and this is just whenever tissue cells are unable to use the amino acid phenylalanine. So while this can be seen in high protein foods like milk and eggs, they're best known, or phenylalanine is best known for being seen in artificially sweetened products like gums and sodas. And so individuals that have this genetic mutation don't have the ability to metabolize this amino acid, and so it can build up in the blood and actually early in life begin to slow the development of the central nervous system and neuron pathway development, and so that can be associated with mental retardation in young children. Similar thing happens here with galactosemia, and this is where you're looking at things like glucose 6-phosphatase and other enzymes which are associated with the conversion of galactose to glucose. In this situation, they become abnormal or deficient, and so galactose very specifically starts to accumulate to the brain in the brain in itself, and can lead to mental deficits, kind of like PKU can do. And then, of course, you have glycogen storage disease. I apologize. This is the one that's associated with glucose 6-phosphatase. This is what's going to prevent you from actually converting stored glycogen into glucose. And so one of the byproducts of this is, of course, you have individuals who have diabetes mellitus-like symptoms, even though there's no problem with insulin. And at the same time, you start to see enlargement of the liver and the skeletal muscles as they continue to accumulate more and more glycogen in themselves. And so a couple of questions here. During the absorptive state, excess glucose can be stored in the liver through the process blank. Question 8. During the post-absorptive state, fat stores undergo lipolysis, yielding glycerol and fatty acids. The fatty acids can undergo beta oxidation to yield blank. And if these are not used by the Krebs cycle, they will be converted into blank. And that is the end.